presentation. My name is Dr. Fangyi Liu, and I am an assistant professor at the National Painting University of Science and Technology in Taiwan. Today, I am very excited to share our latest research titled, Who is the Traitor? A Byzantine general's governance mechanism for overcoming ESG transition barriers in family agribusinesses. This study bridges the gap between family sociology and distributed computing systems to solve a very real sustainability problem. Let us begin with the background and the core issue, which we call the family agribusiness gridlock. Family-owned agribusinesses are unique because they do not just chase pure profit. Instead, they prioritize what literature calls socio-emotional wealth, or SEW. These are non-financial, emotional assets like family reputation and legacy. Unfortunately, this often triggers severe internal resistance when the company tries to implement strict, transparent green transitions. Furthermore, because of internal generational gaps and overlapping equity ownership, the business often splits into competing kinship factions. When this happens, important decarbonization and sustainability data modeling become completely paralyzed by internal vetoes, emotional bargaining, and localized information hiding. This creates a severe ESG bottleneck. Slide 3. This brings us to our problem statement, kinship greenwashing fraud. To preserve public reputation without giving up internal family profits, specific sub-factions or untrusted subcontractors might intentionally falsify carbon logs or financial metrics. They practice internal greenwashing. Traditionally, family businesses try to resolve conflicts through centralized authority, like patriarchal dictation or subjective mediation by elders. But under acute emotional conflict, this centralized trust breaks down entirely. Therefore, there is a critical research gap. We desperately need an objective, automated, and fault-tolerant governance system that can filter out deliberate data noise within these human-centric family structures. To solve this, we propose a theoretical framework that moves us from family feuds to computational fault tolerance. Our logical premise is simple. If family factions act like decentralized computing nodes, we can use cryptographic consensus algorithms to mathematically enforce honesty. Let's look at our mathematical mapping. We map board members, family factions, and contractors to network nodes, denoted as lowercase n. Factions that falsify ESG metrics are treated as malicious traitors, denoted as lowercase f. Traditional patriarchal arguments represent subjective vulnerability, and our ultimate consensus objective is to create an unmanipulated, verified corporate sustainability ledger. Here is an overview of our proposed three-phase algorithmic architecture. Phase 1 is dimensionality reduction. We take high-dimensional, complex socio-emotional family profiles and compress them using TSNE nonlinear processing. Phase 2 is faction partitioning and weighting. We use k-means clustering to identify operational alliances, and then apply a geometric contraction expansion voting weight engine based on family bloodlines. Finally, Phase 3 is consensus execution. We use a modified Byzantine fault tolerance protocol to achieve absolute validation of our environmental and financial ledgers. Let's dig into the mathematical modeling of Phase 1, which focuses on high-dimensional kinship profiling. Before any algorithm can resolve conflict, we must first quantify family dynamics. We characterize each family nodi by a d-dimensional profile vector written as x sub I in r to the power of d. As you can see on this slide, the vector x sub I equals, inside brackets, g sub I, e sub I, sew sub I, and p sub I. Let's break down these feature elements. G sub I is the generation gap index measuring the distance from the original founder. E sub I is the percentage of equity ownership shares. SEW sub I is the socio-emotional wealth priority scale. And P sub I represents the financial profit interest alignment matrix. Now, why use TSNE for dimensionality compression? Traditional linear methods like PCA fail because they cannot capture complex, nonlinear human social relations. Therefore, we apply t-distributed stochastic neighbor embedding to map these multidimensional profiles to a low-dimensional space, denoted as y sub I and y sub j in R squared. Look at equation 1 for the high-dimensional joint probability distribution. The conditional probability p sub j given I is calculated as the exponential of minus the squared Euclidean distance between x sub I and x sub j, divided by 2 times sigma sub I squared. This is then normalized by the sum over all k not equal to I of the same exponential term. The symmetric joint probability p sub I is simply p sub j given I plus p sub I given j, all divided by 2n. For the low-dimensional mapping, equation T utilizes a student T distribution manifold. Here q sub I equals the inverse of 1 plus the square distance between y sub I and y sub j, divided by the sum over all pairs of the same inverse student T term. This specific layout prevents crowding and highlights distinct social groups. To optimize these low-dimensional embeddings, we minimize the mismatch between our high-dimensional and low-dimensional probability distributions. We do this using Kullback-Leibler divergence minimization, or KL divergence. Equation 3 shows our objective cost function. We want to minimize capital L, which equals the KL divergence of P parallel Q. This is computed as the sum over I not equal to J of P sub I times the logarithm of P sub I divided by Q sub I. The logical outcome of this optimization loop is fascinating. Family nodes with identical emotional and financial motivations will mathematically gather closely together in the 2D coordinate structure. On the other hand, conflicting generations and competing alliances are forcefully cast apart in the data space. Once we have our optimized coordinates, we move to phase 2, partitioning and the bloodline weight engine. First, we apply unsupervised k-means partitioning. The compressed coordinates are grouped into capital K factions. As shown in equation 4, we find the argument that minimizes the sum over capital K clusters of the sum of square distances between y sub I and the cluster centroid mu sub k. The centroids mathematically locate the operational core of competing alliances. Second, we use a geometric contraction expansion model to allocate consensus voting weights, written as W sub I. Corporate authority changes based on seniority and ownership, so we use equation 5. W sub I equals W base, multiplied by a fraction of 1 over 1 plus theta times G sub I, and then multiplied by the exponential of psi times E sub I. Our constraint is that the sum of all W sub I must equal exactly 1.0. Here, theta is the generational decay contraction factor, and C is the equity scaling expansion multiplier. Now we reach phase 3, the 3F plus 1 fault-tolerant ledger validation. All environmental data and carbon transaction logs undergo decentralized validation across our weighted node groups. Look at equation 6, which outlines the classic Byzantine security boundary constraint. The total number of nodes, n, must be greater than or equal to 3F plus 1. This implies that the maximum number of allowed malicious traitors, F, is less than or equal to the floor function of n minus 1 divided by 3. This provides a powerful governance guarantee. Even if up to lowercase f malicious factions, which can be up to 33% of the entire network, deliberately try to falsify carbon credit logs or hide profit margins, the algorithm guarantees consensus. It filters out the data noise and enforces a single, valid reality without relying on any central patriarchal authority. To prove that this mathematical framework works, we built a comprehensive simulation and validation pipeline. Our test environment relies on 3 main pillars. Pillar 1 is synthetic data profiles. We generated 1,000 synthetic multi-generational family tree graphs. These graphs are designed to explicitly mirror complex equity structures and historical governance feuds. Pillar 2 is the real-world empirical layer. We seeded our simulation with actual carbon tracking logs collected from active agricultural operations. Finally, Pillar 3 is our conflict injection scenario. We simulated acute socio-emotional conflict settings where up to 30% of the nodes act maliciously by injecting fraudulent, low-emission metrics to mimic corporate greenwashing. To rigorously evaluate our model, we established 3 quantified assessment benchmarks from information theory, ecology, and network science. The first benchmark is information entropy, denoted as capital H. This measures the uncertainty and chaos of corporate data across our network. Our goal here is simple: lower is better, aiming for zero noise. The second benchmark is Simpson's Diversity Index, denoted as capital D. This evaluates the distribution balance of power among family factions to make sure we avoid what we call the tyranny trap. For this metric, higher is better, indicating an optimally balanced power structure. The third benchmark is community conductance, denoted as capital C. This quantifies the isolation, friction, and resistance levels between competing factions. Here, lower is better, representing seamless fluidity in communication. Let's examine the main experimental results under our acute conflict scenario, where 30% of the nodes are acting maliciously. This table compares three different approaches: traditional patriarchal management, standard majority rule heuristics, and our proposed Byzantine governance model. Look at the data. For information entropy, traditional management scores a very high to 0.84, showing high chaos. Standard heuristics drop it to 1.95, but our model reduces it down to just 0.41. For Simpson's Diversity Index, traditional management sits at a monopolized 0.31, while our model achieves an optimally balanced 0.88. For community conductance, traditional systems suffer from high friction at 0.72, whereas our model achieves an incredibly low 0.12. Most importantly, look at the data verification accuracy. Traditional models only get 62.4% accuracy, and standard heuristics reach 71.8%. Our proposed Byzantine model reaches a near-perfect 99.6% verification accuracy. Let's visualize these findings to understand how our model neutralizes friction and suppresses noise. On the top left graph, you can see the information entropy transition. Traditional structures suffer from extreme data fragmentation, keeping entropy high. Our model successfully suppresses entropy from 2.84 down to 0.41, confirming that fraudulent greenwashing claims are successfully filtered out of the system. On the bottom left, the pie chart shows our power distribution balancing. Traditional models trap governance in a low diversity monopoly, but our algorithmic inclusion stabilizes the Simpson index at 0.88. This gives a fair voice to secondary stakeholders based on objective math rather than family politics. Finally, on the right, our network diagram shows community conductance. High conductance usually causes major tracking gridlocks, but automated weighted consensus reduces this friction to 0.12, effectively clearing communication bottlenecks between rival factions. To summarize, let's review our core contributions and future horizons. This study delivers three key contributions. First, it introduces a unique socio-technical innovation by mapping complex family sociology into an objective, fault-tolerant distributed computing network. Second, it creates a robust mathematical pipeline that unifies TS and K-means and 3F+1 Byzantine protocols to actively neutralize greenwashing fraud. Third, our empirical validation proves that we can achieve 99.6% RCNTSG data accuracy even when 30% of the network acts maliciously. Looking ahead, our future scope includes upgrading to asynchronous practical Byzantine fault tolerance, or PBFT architectures, to handle real-time carbon data streaming from smart farms. We are also working on smart contract integration, deploying zero-knowledge proofs, or ZKPS, to protect sensitive family privacy while proving absolute ESG compliance to external auditors. Thank you very much for your time and attention.